Hello, it's Keith here, and this is lesson 82 of the platform-specific series of my Z80 assembly programming tutorials. And today we're back on the Sam Coupe again. Now, we looked at Mintile in 16 colours last time, and this time we're looking at the 4-colour version. But wait a minute, I hear you say there's more than 4 colours on that screen. What magic is going on? Well, the 4 colours refers to the pattern data, the data that's actually used for the source of the graphics. What I'm doing here is I'm taking the 4 colours and I'm tinting them using one of 4 possible palettes. So I'm using the full 16 colour screen, but the source data is only 4 colour and thus uses half the memory. Now, I think this is worth considering because on the Sam Coupe, one of the problems you tend to come across is the fact that you have to deal with page flipping, and the screen bank is awfully large. The screen is 24 kilobytes, but the bank switching works in 32 kilobyte blocks, and so this becomes a bit of a pain. And so by making the pattern data as small as possible, you might not need any bank switching. If your program can fit within 32 kilobytes, you won't need any. And so, as I say, I think it's worth considering using 4 colors and shading them in this way. And it's personally quite good for me because I'm porting my games from the Amstrad CPC, which is a 4-color system anyway. And so this allows for a more consistent style across the systems, and I quite like the 4-color tinted effect. It reminds me a bit of the Game Boy Color and things like that, where you've got 4-color palettes for each sprite, but the sprites each have their own particular shade. So we're going to have a look at this today, and this is based on the original 16-color version, but it's been quite heavily tweaked for the 4-color mode. Now, the original version actually converted the 4-color source data to 16-color screen data in real time. Found that was extremely slow and didn't work so well when I was doing my this was used for Chibi Fighter, my little test game originally. And so what I've done is I've actually used an even bigger lookup table. Now, before we were using a 256 byte lookup table for the X-flipped source data. Now, if you think about it, one source byte with 4 colors will be converted to 2 screen bytes of 16 colors, because there's 2 bits per pixel in our source data and 4 bits per pixel in our destination data. Now, rather than do the conversion via bit shifting, what I've actually done is I've created a lookup table with 2 entries per source byte unflipped, and that's converting the 4-color data to 16-color equivalents, and then a second 2 bytes for the equivalent X-flipped versions. And so there are effectively 4 bytes for each possible source byte of the pattern data, 2 for unflipped and 2 for flipped. By doing this, it's much faster because the conversion's all been done in advance, and so we're just using a lookup table in both cases to do both the 4 to 16 color conversion and the X-flip if required. Okay, so that's what we're going to do. Now, like before, we're running from memory address 0 or memory address 100 if you prefer. We're using the lower memory area. This is ported directly from my Chibi Fighter game, which had music, and that music was being done by an interrupt handler at memory address 38, so that low memory area was very convenient, and the 8000 onwards range is being used by the screen in the exact same way as before. Now, we're defining our lookup tables here, and so basically these are the addresses that will be used for the 2 lookup tables. Now, what we're going to do is we're going to build the lookup tables here. So we're loading the HL address with fliplet, and what we're going to do then is we're going to take the low byte, which is the byte we want to convert. Now, we're going to ink the H part of the HL pair 3 times, because depending if H has 0 added to it, 1 added to it, 2 added to it, or 3 added to it, this will select the 4 possible bytes out of the 2 bytes for the unflipped and the 2 bytes for the flipped. And so we're switching between them by just manipulating the H byte. So we're loading the L byte, that is the value we want to convert here. And then what we're doing here is we're basically taking 2 of the bits out of the L byte and we're shifting them into the correct positions for the destination screen memory for the first byte here. Now, this is basically the top 2 bits, bits 6 and 7 are 0. The next 2 bits are one of the colors. The next 2 bits are 0, and the next 2 bits are the second color. Using 4 colors for our screen data. Now, when it comes to later, we'll see how we're actually tinting that data to use the full 16 color palette, albeit only 4 colors per sprite or 4 colors for the background. So here we're doing the first 2 pixels 1 byte. Now, once we've done the first byte, we're inking H, and we're doing the same for the second byte. Those are the 2 unflipped bytes. We're then inking H again. This is now the 3rd byte in the lookup table, and this is the X-flipped version of that same data. So this time we're loading the byte in again from L here, and we're this time doing the flips. We're shifting the bits in the opposite direction so the 2 pixels are reversed. And then we're storing that into the lookup table, inking H, and doing the final byte of flipped data there. So we've now got 4 bytes for each entry in our lookup table. We switch between the bytes by inking H, and we select our byte that we want to flip by setting the low byte of the lookup table address, like we did last time. If you've seen that, if you've not, don't worry, we'll look at it in a moment. Okay, so that's building our rather substantial lookup table there. Now let's take a look at our palette. So our palette is a 16 color palette, but we've split it into 4 blocks. So colors 0 to 3 are the first of these so-called tints that we have here. Then colors 4 to 7 here are the second one. Colors 8 to 11 here are the third one, and 12 to 15 are the final of the 4 tints. So these are the 4 possible palettes that we have, and we're using these for things like the background and the 2 Chibikos. That's why they're different colors. Now, when we actually want to apply these tints, what we've got is we've got a byte in memory called tile tint, and what we do is we load in a byte that will be basically ORed into the data that is loaded to the screen just before it's completed. So basically, you can see 2 of the bits there are 1, 1. That is the tint, effectively selecting one of those 4 tint palettes. The bits that are 0 there are the ones that are being loaded in from the actual pattern data after it's been converted. So this is using tint 3, this is using tint 0, and this is using tint 1, but if we changed it, if we took that bit out there and put it here, we would now be using tint 2. So basically, we're very simply setting 2 of the bits of the destination screen memory. We've got our get screen pos routine here, which calculates the VRAM destination from our XY position. Our XY position are in logical units, that's pairs of pixels, and the screen uses 2 pixels per byte, and so it's very easy for us to work out the VRAM destination there. That's used for the sprites. The sprites are miniature tile maps effectively. It's the same code doing both jobs. We've got a miniature tile map here, which is the Chibiko sprite, and that is used to draw Chibiko to the screen. Okay. Now, when it comes to drawing our objects to the screen, whether it's the entire screen or whether it's just a little sprite, we do it in strips horizontally. So the multi-platform code will call doStrip, and that will actually draw the strip to the screen, and it does that, drawing the entire sprite to the screen. So doStrip here will do our drawing, and what we're doing here is we're loading tile tint into IXH here. That is the tint that we want to apply. Unfortunately, we had no low registers left. Now BC is going to be our lookup table, so we're loading B with the high byte of the lookup table here, and C will be loaded later. Next, what we're doing here is we're loading in our tile number that we want to show. A value of 0 here is either a transparent part of a sprite or a part that hasn't changed to the background. The background tile map is actually a cache, so we set the bytes in that to 0 once they've been drawn to the screen, although we would self-modify that and disable it if we are drawing sprites, because we want to keep those intact so that we can draw them again later. Now, what we're doing here is we're effectively calculating the multiplication of the tile we want to show, and we're calculating the source data in the pattern data here. Now, so we're effectively multiplying the tile number by 16 here. Why 16? Well, because we're using 4 colors per tile now, and so each byte will contain 4 pixels, and so there's 2 bytes per line, and there's 8 lines, so that's 16 bytes total. So we are calculating our VRAM destination here, but we're not using stacked misuse this time. This is the version that was used in my Chibi Fighter game, and that used the interrupt handler for music. And because interrupts on the Sam Coupe will disappear if interrupts are disabled when they occur, that would cause the music to slow down. On a system like the Amstrad CPC and the Master System, if interrupts are disabled, the interrupt will immediately fire once they're re-enabled. But on the Sam Coupe, like the Spectrum, that's not the case. So we're actually keeping interrupts enabled this whole time. My interrupt handler for my music software doesn't require shadow registers, so we don't need to worry about that. And so what we're doing here is we're loading the first byte of our source data from HL, and basically we're loading that into C. Now, if you remember, we loaded B with the top byte of the lookup table address here, and so once we load C with this byte here, we now have the lookup table pointing to the conversion data for this byte. Now, it's the first 2 bytes that will be the unflipped data, which is what we want here. So what we're doing here is we're loading in the first byte from BC, we're ORing in the tint, and then we're writing it to the screen. Now, if you only literally wanted 4 colors on your screen, you could remove that OR. That would save a little bit of speed, but that wouldn't get these nice tints. I do like the tinted style here. As I say, the 4 color sprites I think make things look quite stylized. That tint is being applied there, and the sprite is being written to the screen. We're then incrementing E, moving across the screen by one byte, and we're incrementing B. Now, B is of course pointing to the lookup table, and so C is pointing to the data we want want to convert. And by inking B here, this is now pointing to the second byte of the conversion of the 4 color data. So we then load in that second byte or in the tint and write it to the screen. We then ink E, moving across the screen, 1 more byte, and then we decrement B, moving it back to the original position. We then load in another byte to convert into C. We then repeat that, loading in the first byte from the conversion table BC, oring in the tint, writing to the screen, moving B to the second byte, moving across the screen, and we repeat again, transferring more data. Now, because we're using BC, we can't do any clever memory saving of calculating our VRAM destination, so we're moving down a line here, and then we're just simply repeating over and over again, incrementing D as required for our DE destination in VRAM. And we're just repeating. This is a massive unwrapped loop. The reason for that is I was having performance issues with my game, so I've chosen to use all the memory. If you wanted to have a loop counter, you could do that, but as I say, for me, the memory wasn't the priority, the speed was the priority in this case. And then once we've completed a line, we're basically decrementing D, moving the VRAM destination back to the top of the tile. We go across and down, drawing the tile and then jump back up. Then we move across to the next tile, and then we repeat until we've done the entire line. Now, once we've finished, basically all we do is we are returning. This is the code to handle empty tiles. That's just skipping over the current tile and moving across to the next line. And then finally, we have the do strip reverse routine. Now, actually, this is pretty much identical. The only real difference is the way that the screen movements are occurring. So before, after each byte was written, we were incrementing the E byte, the destination VRAM, and after each tile, we were incrementing BC after we'd read in a tile from the tile map. But this time we're doing the opposite. So we are now decrementing the E part of the VRAM destination, and we are decrementing BC after we read in each tile, and that's because we are flipping the data. Now, of course, the other thing we're doing is we are flipping the bytes, the pixels within the bytes that we're reading. Now, actually, all we need to do this is point to our alternate lookup table. Remember the first two bytes in the lookup table, B and B+1 if you will, these were the unflipped data, but if we use B+2 and B+3, these are the X-flipped versions because of the way we calculated the lookup table. So now all we need to do is do the exact same thing we did before, loading in a byte from the source data into C, loading in a byte from the lookup table, which is now the X-flipped version of that data, oring in the tint, writing it to the screen, moving left across the screen, incrementing B of the lookup table to move to the second X-flipped byte, and doing the same, moving back to the first entry in the lookup table, moving left across the screen again, and repeating. So I think this is a quite interesting example of a very large lookup table and how it can actually give us some quite good performance. Now, it certainly wasn't my plan to use a lookup table this big. It was kind of an act of desperation, I guess you could say, because the game was extremely slow compared to the other systems. The Amstrad CPC version was the first version I wrote of Chibi Fighter. The Sega Master System extremely fast because it's got hardware. The Spectrum Next has got this massively fast processor, so it always kind of wins in that. But the Sam Coupe has a bit of a problem because it's got this big screen. It's got this 24 kilobyte screen compared to 12 kilobytes on the Amstrad CPC, so there's a lot of data to push around, but its processor is only 50% faster, so it tends to be slower than the Amstrad CPC, and so it really showed. So there was no spare resources to do real-time conversion of the data using bit shifts, and so this lookup table was the only real way I could figure out to actually get the data converted. But anyway, as I always say, go to the website, down the source code, the build scripts, use them if you can. If you can't, maybe you can learn from them. Maybe this will give you some ideas of ways to use lookup tables. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.